thermodynamics. In a point I'm sure that's a violation too.
Because it encourages other people.
Exactly.
So
It's
not just the appearance of it.
Exactly. It's just as bad.
You can make a show of checking.
You people take it.
I need a uniform. Okay, I try.
You go out to the coffee break and watch something. Anyway, whatever. It's empty.
Okay.
Maybe I'll write
Friday, yeah. Figure out. Friday, it is no 7.
All right, everybody, I'd like to get started. So welcome to this afternoon session. The first talk of the session will be by Mika Göös. Right? And he's going to talk about the extension complexity of independent separators.
Thank you. Well, thanks for inviting me. So I was asked to talk about this work I have with Rahul Jain and Thomas Watson. It's appeared in Fox 1 year ago. And we basically have just one main result. So it's just good to come out and say what it is. So we construct a family of graphs that have nearly maximal extension complexity for their independent set polytopes. So the main theorem, just to spell it out, that there exist n-node graphs such that the independent set polytope, I use this notation. I guess some people call these stable set polytopes. They have nearly maximal complexity. Maximal complexity would be exponential in n, but we come only almost there. So it's exponential in n over log n. So if you think back to the first lower bounds we had for extended formulations in this work of Fiorini and others, like optimal lower bounds for correlation and TSP, and we had lower bounds for matching. From those results, you can get by reduction some lower bounds on independent set polytopes. And they would be exponential in root n. And in fact, prior to this result, there wasn't explicit 0-1 polytopes, so that's convex hulls of 0-1 sets with extension complexity larger than root of the ambient dimension. So this is the first that kind of breaks this root n frontier. And yeah, it's almost maximal. So we know from Rothfuss's counting argument that, well, there are doubly exponentially many 0-1 polytopes, so most of them require description length exponential in n, and by a refined counting argument, you can conclude that most of them have exponential in n extension complexity. Well, we don't quite match that, so it's kind of an artifact of our proof that we do need this log n in the exponent. It's annoying. You'd like, of course, an optimal result, but more so here because independent set polytopes are often starting points for reductions. So if you're optimal here, you'd be optimal for many other problems. Also, without log n, you could say that you proved the exponential time hypothesis for extension complexity, but we're not quite there. And I think Sebastian tells me that if without you didn't have the log n, then you would start developing a kind of a PCP theory inside extension complexity. Again, one more motivation to get rid of that. So that's the main result. And since this is ancient work, 1 year ago already, so I thought, how can I make this exciting for me as a presenter? So I thought I'll actually also present a kind of a bonus result, which we realized holds after we got this. And that's in the regime where we put some bound on the independence number of the graph. I should maybe thank this guy, Austin Buchanan, that asked us whether our methods give anything in this regime. So here's the bonus result. That again, if you consider n-node graphs, and you put some bound on the independence number. So you should think of this as kind of the fixed parameter tractability setting, where the size of the independent set is the parameter. So let's say the independence number of our graph is some k, which you should think of as a large constant, or formally this result holds up to k being some small polynomial. Something like this. Then what's the extension complexity of independent polytopes? For these kinds of graphs, well, there are at most n choose k possible independent sets. So the trivial upper bound is n to the k, and that's what we can match exactly. Equals n to order k. So yeah, it's a kind of a fixed parameter tractability setting, and it's known by reductions that if you have bounds like this, you can get something in this regime. Even the Turing machine setting, there are reductions that say, if you assume that the exponential time hypothesis holds, that SAT requires 2 to the n complexity, by reductions you could get something in the fixed parameter setting. And those reductions work even in the extension complexity setting. In particular, if you applied such reductions to this result, you would get a lower bound here that's n to the power k over log k, because of this annoying thing. So this result then is kind of incomparable to this. But it's nice to get something optimal at least. So I think today I'll, so both are proved by a similar high-level approach. But it turns out this is a lot easier because we can, at a crucial technical point, rely on what I call these query-to-communication lifting theorems. So I'll mainly maybe sketch the proof of this guy and then tell you where the two proofs diverge. And it's going to be a very chillaxed lecture. It's mostly about reductions. I'm not going to delve too much into technicalities here. But I think reductions are important here because, ironically enough, graphs are so expressive that it's not even clear where you would start to look for the hardness of an independent set polytopes. There are too many possibilities. It's this problem of too many choices. So the reductions, they identify a hard core, like some plausible hard setting for an independent set polytope. And it kind of conceptually solves the problem. So then you can, maybe if I've shown you the reductions, you can kind of sit down and start using all the available technical tools like information complexity and what have we to actually prove like numerically some lower bounds. But yeah, mostly about reductions today. Okay, so this is maybe the thing to have in mind. And okay, so since I have you here, I also want to advertise another set of results about independent set polytopes we have in some related papers. And those have to do with an interesting submatrix of the independent set polytope. So it's already Yanakakis defined this thing called clique versus independent set. So these are the slack matrix you get out of so-called clique inequalities. So let me just spell this out. So called the clique versus independent set. Okay, and I'm really defining a submatrix of the slack matrix of an independent set polytope. But I'm using communication language because that's what I like the most. It's more active language, more algorithmic maybe. So I say Alice, which really holds a vertex of an independent set polytope. So Alice receives an independent set in the graph. So again, we have some n-node graph. Alice holds an independent set. And Bob, this is the object that it will define an interesting linear inequality for the polytope, holds a clique. And the interesting inequality is just that any independent set can only contain at most one node from the clique. So you can write this out as a linear inequality, like the sum of the nodes of y, or those coordinate analysis indicator vector, should be at most one. So another way to say this is that the intersection of these two sets, if you use the set notation, is at most one. So okay, the corresponding slack is just then, well, you have to be careful here to get it right. So it's 1 minus this quantity. It's a non-negative thing, 0 or 1. So one reason this slack matrix is interesting is that it captures, well, the non-negative rank of the slack matrix captures the extension complexity of independent set polytopes when G is perfect. And Yannakakis already in his paper showed that that this matrix has relatively small non-negative rank. So for every G, not only perfect, but arbitrary graph, the non-negative rank is at most quasi-polynomial. So n to the log n. So in particular for perfect graphs, that's a bound on the extension complexity. And the major question is this the best, or can you have, say for perfect graphs, polynomial extension complexity? Well, this remains open, but what we have proved in some related work is some lower bounds on the non-negative rank for general graphs. So one thing we can show is that there are graphs, again, not perfect, where, well, not only the non-negative rank, but even the cover number, which is asks how many rectangles do you need to cover all the non-negative entries. It's a lower bound on non-negative rank. So cover number can be super polynomial. So n to the log something like 0.1. So this is a few years ago, and I should mention that just this year at ITCS, this was improved a little bit to 0.2 by David Hatami and Tal. And I guess the conjecture is that this really should match the upper bound. That's my conjecture. It's clearly converging towards it already. But so that's a cover number. We can achieve nearly the optimum if you not only look at the cover number, but the whole, like the original question, the non-negative rank. So again, there are graphs where non-negative rank is at least n2, and okay, so there are some loss, some log loss in the exponent. And this result, it's hidden in a paper I have with Jairam, Tony, and Tom. And okay, I hesitate, like, is it 15 or 17? We had like 2 years to get this published, but it did appear in iCalp this year. And the way the main results of this paper are expressed is as studying the randomized communication complexity of this, understood as a decision problem. But in fact, the proof is strong enough that it proves a lower bound even for the non-negative rank. In fact, slightly stronger. It's even for the approximate non-negative rank, which means that not only is the non-negative rank low, but even if I'm allowed to perturb the entries here by 1% point-wise, the non-negative rank is still high. So approximate non-negative rank, lower bounds, randomized communication complexity actually. And that's the method we use there. So I think these are all the results I wanted to advertise, and for the rest of the talk we'll be just going into seeing how this is proved. I should mention, these results are also obtained using similar tools, but very different reductions. So it's all about this interplay between query and communication complexity, as you'll see. So any questions about the results? Excuse my flu. So I'm on flu medication, but it is fine. The audience is a little wobbly today, but we'll manage. So this identified an interesting submatrix, and I maybe want to approach this result similarly, identify an interesting submatrix of the Slack matrix. And kind of half tongue-in-cheek, in analogy with click versus independent set game, I call what follows an independent set versus independent set game. So this is the source of hardness for this result. Okay, so this is a game. Again, we have a graph. But now let's say that the vertices are partitioned into left and right pieces. The graph is not bipartite, it's just that we've split the nodes. And I'll assume that the independence number of this graph is bounded. So this k is the same k as there. So I can now define an interesting, well, it's going to be a search problem for starters. So here, this is an independent set. So it's from the left-hand side of the graph. And the set has size k. Okay, and Bob is very similar. Y from the right side of the graph. So Alice and Bob have k-sized independent sets on left and right, and I've kind of syntactically made them disjoint. So the union of these two guys is a set of size 2k. But I'm assuming the independence number is smaller. So it means that there must be an edge between Alice and Bob sets. And an associated search problem is to find such an edge. So find an edge that crosses the two sets. Except I'm going to write it down a little bit awkwardly. I'm saying find an Alice side of the node of such an edge. So find a node V in Alice's set that's adjacent to something in Bob's set. So N is here, is all the neighbors of Y. So I've set this up in such a way that this set is always non-empty. And I think in my abstract I talk about a connection between extension complexity and circuit complexity, or monotone circuit complexity. I won't maybe use that language here, except to say that monotone circuit complexity or monotone circuit depth can be characterized in a communication language. And it's all about search problems in communication complexity, and this is a search problem. So the connection which is crucial to these results is that from any search problem, there's a very nice associated Slack matrix, or at least a non-negative function defined on this domain, that simply expresses the fact that our search problem is total. So for any x and y, this set is non-empty. So I'm going to use a red arrow. So this is a connection that was introduced by Rubesh as some extension of something that Rasparov did. Well, we're doing it for a single search problem, but you could do this for anything. But whenever you have a total search problem, it's a very kind of a non-trivial fact about it is its totality. It's the fact that, and I call this now the Slack, is the fact that this set is empty, so it's non-empty. So this is of size at least 1. Or in really Slack form, the number of witnesses or solutions to the search problem minus 1 is a non-negative quantity. So this will be our Slack, but we need to be careful. It's picked from the slack matrix of the independent set polytope of the left side of the graph. So this is in G induced on the left nodes. So again, X is now an independent set in the left side. And I've identified here a bunch of interesting subsets of the left-hand side that must intersect every k-independent set there. So I can write this linear inequality that says this, there's an intersection, says this linear form is at least one. Okay, there's more. I mean, this definition was, of course, inspired by this, but there's more. So it turns out this search problem is at least as hard as this. So here I'm maybe asking for the deterministic communication complexity of solving the search problem. Here I'm asking what's the non-negative rank of this slack matrix. And I claim that if you have an efficient deterministic protocol, you immediately get an efficient non-negative rank decomposition. And again, this is this argument by Schrubesch. And I'll explain it in words. It won't be terribly important, but how do I go from a deterministic protocol here to a non-negative rank decomposition? Well, firstly, let me use this language I really like of characterizing non-negative rank, or really the log of the non-negative rank, I guess, in terms of a communication complexity language. I think this was discussed earlier. So the log of the non-negative rank of a non-negative matrix is the least cost of a randomized protocol that computes this matrix in expectation. People heard about this characterization? I maybe like to say more in a self-documenting manner that what we are supposed to do here to give a non-negative rank decomposition is to design a randomized protocol whose acceptance probability, so the protocol always accepts or rejects, but the probability which it accepts is proportional to these non-negative numbers. So now the numbers are integers, but if you scale them down small enough so that you can interpret them as probabilities, then they are indeed acceptance probabilities of some efficient randomized protocol. So really I'm claiming deterministic solution here implies a randomized protocol whose acceptance probability is proportional to this number. And the argument is really simple, 2 steps. I assume I have a protocol here, so what can we do? We run it. We find a witness in one of these guys in this set. So we have this in our hand. And the second step of the protocol, we have to introduce randomness. What we do is we sample a uniform random node from Alice's side, distinct from the one we found. And then we check, is this node we sampled, is that another solution to the search problem? So really, it's this thing that we found in the first step. That's the -1. The second stage of the algorithm is just going to accept a probability proportional to how many other witnesses are there for this search problem. So it's a nice connection, but somehow it goes in the wrong direction for us because we really wanted to prove lower bounds. We want to show this has large non-negative rank. But the connection doesn't give us anything. It goes the wrong direction. We'd maybe like to say that if the search problem was hard, then automatically this is hard. But that's the wrong direction. In general, you can't hope for this converse to hold. There are examples for other search problems. But it does say, and actually it was known in previous work, that search problems of this kind are hard, not only for deterministic protocols, but even for randomized. That this connection says we need to strengthen existing results. But this is kind of already a hardcore, that if this is hard, you might hope that you get lucky that the associated slack matrix is also hard. Okay. So this doesn't still solve the conceptual puzzle of, what's the graph going to be? I haven't really constructed a graph. And so that's what we're going to do next. The inspiration for constructing a graph is now from this simpler model of query complexity, not Alice and Bob communicating, but a simpler model where it's easier to prove analogous results, lower bounds are easier to prove. So I was a bit unsure how this audience, whether you know about query complexity. So this study of decision trees that get as inputs just one string of bits, and they're allowed to query individual bits. So you could view what I now say in that context. So I'm going to introduce, it's a very well-known hard search problem in the context of query complexity. And we'll end up, in the end, somehow reducing it to that and carrying the hardness with us. So this is a search problem that's this is inspired by one of the most widely studied CNF contradictions in proof complexity. So we call it the Zeiten search problem. So firstly, traditionally, these Zeiten contradictions, they're just unsatisfiable CSPs with XOR constraints. So it's just some name that proof complexity people like to attach to this. So you can define them relative to any graph, but let me pick a hard graph. So take a 3 regular expander. Okay, on some set of nodes and edges, and now the parameters are such that I have k edges. Okay, since it's regular, I will have order of k nodes. It's a sparse graph. And I define an unsatisfiable XOR CSP by interpreting each node of the graph as a parity constraint on its incident edges. So I have maybe 3 incoming edges, Z1, Z2, Z3. And this is representing a parity constraint. Maybe I'm saying that these guys should sum to 1. So as long as I take my graph to have an odd number of edges, this will be unsatisfiable. It's quite easy to see. I have odd many such constraints with, okay, left-hand side should be right-hand side. Anyway, so if I were to sum together odd many of these constraints, I would get 1 on the left-hand side because it's a sum of odd many ones. On the right-hand side, each variable participates in 2 constraints. So there would be appear twice in this sum, so they would cancel themselves out. So you get 1 equals 0, so it's unsatisfiable. Well, there's a general principle. Whenever you have an unsatisfiable CNF or CSP formula, you can define an associated search problem, where the input, it's a truth assignment to the underlying variables. So here, they're the edges. So input is a truth assignment. And okay, the CSP is unsatisfiable, meaning that on any assignment there are some parity constraints that are violated, that are unsatisfied. And so the search problem is just to find one of them. So find a node that is violated under the input assignment. So this is a set of nodes violated under this assignment. Okay, so these are classically really hard for decision trees. And you can do the same trick as we did there. It's a search problem. We can be inspired and define a non-negative function on our input space that expresses the fact that the function is total, that this set is non-empty. So again, a similar red arrow. And we can define a non-negative function. I shouldn't call it slack. I call it slack in quotation marks because there's no polytope yet. But this is a non-negative function. So it's just kind of matching what we're doing here. And since this is intuitively hard, I mean, people have proved it in proof complexity that deterministic decision trees can't really find these violations fast. And in our paper, I guess, for the first time, we also proved that even randomized decision trees can't find these fast. Well, it's reasonable to suppose that somehow the game where you need to design a randomized decision tree whose acceptance probability is proportional to this quantity should also be hard. And so that's what we show. I should maybe spell out what the query complexity analog of non-negative rank is. I mean, I just kind of implicitly defined it, like the model is randomized decision trees whose acceptance probability you care about. But another way to measure the complexity or define the same notion is to look at its what we call conical Hunter degree. So in suggestive notation, it's let's call this function non-negative function f. So what is this? It's conical Hunter degree. Something that is related to Sher-Rayleigh-Adams hierarchies. So I need to define what a conical Hunter is. Well, it's a non-negative analog of polynomials. So it looks something like this. You are taking us, okay. So this is a representation for a non-negative polynomial function, which is a conical combination. So you have some coefficients that are non-negative of Hunters, or it suffices to say conjunctions of input literals, Ci. So this is a conjunction of input literals. So for example, Z1, Z2 negated. So these are syntactically non-negative components out of which you want to construct your non-negative function. So the degree of such an expression is the maximum width of a conjunction you're using in it. And if I give you a non-negative function, you can ask what's the least degree of a conical Hunter that exactly represents it. So this is kind of the query complexity analog of non-negative rank. And it's for this, this guy that we show hardness. So we can show, and this is not terribly hard. I don't have time to maybe go into it. The proof is like 2 pages, which should be considered relatively simple in this case. Is that for this function, okay, so it has full conical Hunter degree. So somehow this is the source of hardness. I mean, at least here we've proved some results that seem analogous to what we really want, but we need to go there through reductions. I shouldn't say only reductions. There's a major step where you amplify hardness in a very weak model of computation to something in a more powerful model of computation, and that's the next step. So what remains is to do this, go over there, and it's done in 2 steps. And so I have 2 boards in between. Is it coincidence or intelligent design?
So the connection between the extension complexity and this slack matrix, that's standard?
Connection between
The result you just erased, the n to the theta k being implied by the non-negative rank of this particular matrix, is that?
So you're talking about this result. Yeah, so if I can show that the non-negative rank of this guy is n to the order k, then that's equivalent to the main result. Or like this is a particular submatrix that I identified that's hard. Yeah. So the proof from here to the actual main result, the bonus result, should be complete by now. Okay, so the first step is to just somehow come up with some communication analog of this problem that's equally hard. And so that's exactly what these query to communication lifting theorems allow you to do. And Raghu is going to talk about this, by the way, in the next talk. So I'm just going to quickly formulate what it says. So here the input is k bits. There's no Alice and Bob. But the standard way to convert it into a two-party communication problem is to take your problem, let's call it name, like citing problem, search problem, and graph G. So it has these k input bits. And the way we're going to convert this into a communication problem is we're just going to plug into the inputs a small two-party function. So we call it G. So this will be that. So G, call it the gadget. So it takes some inputs from Alice. And let's say it takes log m bits from Alice, log m bits from Bob. It spits out 1 bit. So this would be log m bits. Log m bits, and I have k of these all together. So it is a communication problem. Alice gets all the first inputs, Bob gets all the second inputs, and they're supposed to solve this search problem on input, which is the output of the gadgets. And the intuition is that if you choose this gadget carefully enough so that it's complicated for protocols to compute, that they need to spend some bits of communication to even figure out what the output of a particular gadget is, then the composed problem, the lifted problem, intuitively it's hard. I mean, you don't even know what the inputs to the outer object here are before you communicate enough information about the inputs. So it's literally as if you wanted to query a particular input, you need to spend communication. So that's exactly what a lifting theorem formalizes. Now the choice of the gadget is left to the lifting theorem. You want to choose it to be small. Presumably, you want the complexity of this guy to be dominated by the query complexity of the outer object. And so far, these lifting theorems are known, and we're going to use them when G is the inner product gadget. It wouldn't really matter for our reductions what it is, but here's one choice under which this works. Just for concreteness, so G on input 2 log m bit strings is just the inner product. I mean, I'm interpreting them as binary strings. It's just this mod 2. Again, it's like a canonically hard communication problem. It just helps to make the following theorem true. So this is the lifting theorem. So this is joined with Shahar Lovett, Raghu Mika, Thomas Watson, and David Zuckerman a few years ago. Raghu is going to talk about a subsequent work to this, which is a bit more sophisticated, but for this we only need the old version of the result. So it says that under this choice of a gadget, you can lift conical Hunter degree into non-negative rank. So I would really be applying it for the associated number of witnesses -1 game. So this would really be F, I suppose. So it says that for all F, non-negative functions, you can characterize the non-negative rank of this lifted problem. So I can identify this with a matrix where Alice's input index is the rows, Bob's input index is the columns. So it's some non-negative matrix. So I guess the formalism is F composed with k copies of the gadget. So the log of the non-negative rank should be the conical Hunter degree of F times maybe the complexity of the gadget, which well, intuitively it should be log m. Like you should spend log m bits of communication to compute a single copy of the gadget. So this is saying that to kind of compute this, you need this many copies of the gadget to be computed. And okay, this would be the ideal theorem, but well, our tools are a little bit blunt, and you can only prove such a thing assuming that not just that the conical Hund degree is large, but a more robust assumption that its approximate conical Hund degree is large, meaning that even to express any function close to f in like L infinity distance, like pointwise 1% approximation, should also be hard. So that's the approximate version of this. Like the least degree of a conical Hund that agrees with f pointwise. So that we can lift into this communication domain. And you even get a lower bound on the approximate non-negative rank out of this. So that's just an application of this type of theorem. But okay, what we get is some kind of a composed problem that doesn't necessarily look like this yet. So the final step is to massage this into a problem of that form.
So what's the relation between m and k?
So good point. So to apply this theorem, you need the gadget to be large enough. So it's important that m here is something like some polynomial in k. So I should mention this is the point where the proofs diverge for the two theorems. The bonus result follows from this because I can use a large gadget. If I had such a theorem for a constant size gadget, m being a constant, not depending on k, I would get the main result, not even without the log factor loss in the exponent, but a maximal 2 to the n lower bound. But we don't know how to do this for constant size gadgets. So for the main result, instead of applying such a thing, we just replace an application of this with an ad hoc argument. Like you compose your Chaitin problem with a constant size thing, and then you just directly analyze it, because we can't rely on a general theorem. Yeah, that's a good point. But yeah, for the fixed parameter setting, large, or not even terribly large, it's like the gadget side in bits is just logarithmic in k. So so it's enough for the bonus result. Okay, so the last bit isn't terribly exciting. It's a reduction that's, many versions of it have been used in the literature. In fact, this reduction is going to look very much like these reductions that say from, let's say, assuming ETH, you can get these results for k-click and so forth. I think all these things go back to something like some reductions of phi-G in the 90s. So, so it's some kind of a NP completeness reduction. Okay, so I'm always going to give these reductions for the underlying search problem with the understanding that you can always do this red arrow thing of getting this non-negative function out of it. So we're looking at this composed search problem. So this is also a search problem associated with an unsatisfiable CSP. It's just the constraints have now been composed themselves with the gadget. So a single constraint in this composed problem is of this form. So I had a parity constraint. But now here, each of these variables is an output of a gadget. Okay, so they take some inputs from Alice. I'll just gather to them on the left-hand side. So some symbol x1, x2, x3, and a Bob input. Okay, y1 up to y3. So it's like now we have a new CSP which is kind of composed. So the new constraints look like this. I have k of them. That was the number of edges I chose for my graph. And now I just kind of need to encode k constraints, you know, that they kind of look like this, independent set versus independent set. And I'll just tell you how to map a single constraint inside this graph. So the graph is again in two parts, on left and right. And for a single constraint, I'm going to insert a click in the graph for Alice and click in the graph for Bob. And these clicks, they are of size m cubed. So think of all the nodes as being in one-to-one correspondence with all possible inputs that Alice might have to that constraint. And similarly here. Okay, so since these are clicks, it just means that in any independent set of Alice and Bob, you only can pick only one node from this click. So these nodes are in one-to-one correspondence with these inputs to the gadget. The natural thing is to define a graph between the two clicks in a way that depends on whether the node left and right together satisfy the new constraint. So, okay, let's say that this node corresponds to some node here, and this corresponds to some node here, and you put here an edge, something like you put no edge if the corresponding inputs do satisfy the constraint. So let's call this new constraint C. So no edge if C is satisfied. So you're essentially encoding the truth table of this gadget as a graph between the two clicks. So that's how you handle a single constraint, but you had k of them. So you just add k pairs. So there are more pairs of clicks. Okay, so altogether k of them. And so you have some graphs here encoding the constraints. And you're also going to add some interclick edges both on left and right. So you want to enforce that a maximal independent set on the left will correspond in one-to-one fashion to some global assignment, k symbols. So you want maximal independent set on the left is in one-to-one correspondence with some. So you introduce some edges that enforce the fact that the partial assignment setting 3 symbols to some coordinates, another 3 symbols here, they need to be consistent. They can't assign same coordinate different symbols. And you're just going to enforce it by adding an edge between every 2 inconsistent assignments. So that's the whole construction. The point is that given an input to this composed problem, k symbols from this set of numbers from 1 up to m, they're in one-to-one correspondence with the maximal independent sets. And since we know that the underlying this Titan problem was unsatisfiable, it means that no matter which k independent set I pick here and here, there will be some constraint that's unsatisfied, meaning the corresponding nodes are going to have an edge between them. So that's basically the reduction. So these reductions, they map witnesses into witnesses in a one-to-one manner. So they, like complexity people would call them parsimonious. And that's the reason why, even though I just gave the reductions for the search problems, you can always go to this non-negative slack function, and they correspond to each other because of this parsimoniousness. Okay, so I think that's pretty much the whole reduction. So any questions about this?
So this is just the FGLSS reduction, but you impose this gadget on top of it?
Yeah, it's basically that, but adapted to a two-party setting. Yeah, so many variations you can do this, but it's essentially the same. But yeah, I guess the point was here that, well, you really start from something that is so simple to analyze, and people have done this in proof complexity a lot. And then by reductions, you're eventually going to embed it into an independent set polytope. And again, it didn't really even matter that it's an independent set polytope at the end. If you had stopped here, it would already been kind of interesting, because you know that you can extract by this red arrow trick some interesting inequalities for some 0, 1 polytope. But maybe you wouldn't have seen that it really is an independent set polytope. Okay, so I think I have 5 minutes left. I'm only going to mention one open problem that I'm really annoyed by, and that's to prove lower bounds for independent set polytopes of matroids, not of graphs, of matroids. Okay, so what's known? I mean, firstly, why would you want to prove that some matroid independent set polytopes are hard? So convex hulls of independent sets of matroids. Well, it would be this is kind of a marketing speech. I feel like it's a natural enough problem in itself, but here's what you could say. It's trivial to optimize linear functions over matroids. Like Creedy algorithm does it. So it would be the ultimate insult to linear programming if you couldn't even do this. However, there's technicality here, which is that there are very many matroids, doubly exponentially many. And again, by a counting argument, you can show that most matroids are hard. But the reason is that they just require so large an description. So we really want an explicit matroid to make sense of this. And the problem is that for natural families of matroids you could think of, there's a line of work that shows that, well, they're actually all easy. You can find polynomial size extended formulations for them. So they're kind of in an annoying place where, well, I have all this machinery I've been developing in my PhD thesis, and I can't start applying them because we don't have a candidate for a hard matroid. And I want to leave you with kind of a nice observation about yet another barrier to proving lower bounds for these matroid polytopes, which I found a bit surprising. So that is that if you look at the counting argument, why are there so many matroids? Well, it's because there are so many paving matroids, and they look like this. So here's your lattice of all subsets of a universe of size n. Everything here, the empty set here. And a paving matroid is basically, it looks like this. There's some level k, so that everything above level k is dependent, everything below k is independent, but within level k you have both independent and dependent sets. You can construct such matroids out of error correcting codes, for example, and by that you can see that there are doubly exponentially many of them. So a counting argument already works for this family of matroids. So you'd think that, okay, if these natural families that people have studied, they don't yield hard candidates, well, here's a family that's certain to have large hard matroids. But there's a formal barrier to exhibiting any explicit such matroid. And that goes back to this connection I didn't really go into, how search problems are connected to monotone circuit complexity. So I'm going to make this claim that if you can exhibit any paving matroid and prove a non-negative rank lower bound for its slack matrix, it implies genuine circuit lower bounds, like circuit depth lower bounds. Not in the monotone setting, but in the fully general non-monotone setting. So this should be quite surprising because we think that, okay, we can prove non-negative rank lower bounds. We just did, and there are lots of methods for them. There shouldn't be any a priori barriers. But in this setting, it turns out that if you just string together a couple of observations that are known about circuit complexity, you can identify this place where we have many hard polytopes, but you can't hope to prove it. Otherwise, you separate complexity classics like NC from NP or something and win a Turing award. So I found this surprising. If you're interested, I've written this observation in the open problems section of my PhD thesis, but it's just one facet of why this problem is so interesting. That existing techniques don't seem to work. Okay, so I think I'll end there. Thanks.
Are there any other questions?
So do you expect that there's a lifting theorem for constant size gadgets?
That's what I conjecture. We don't have any counterexamples, and I optimistically like to believe that they do hold. But yeah, so there are plenty of motivation to do this. Like this is one of the most crucial ones. Other motivations is for monotone circuit size. You could maybe beat the existing, quantitatively the existing records, which are exponential in cube root of the input length, but with this kind of a machinery, you would hope to get 2 to the n. And you would basically redo all of communication complexity. You could prove lower bounds, optimal lower bounds for like set disjointness and gap hamming and all these basic functions if you just had these lifting theorems for a constant size gadget. Plenty of motivation, but it's a hard problem too.
So for the independent set polytopes that you construct, what do we know about the semi-definite extension complexity?
So this family of graphs, they are kind of off-lifted forms. I would imagine that the only SDP lower bounds we have, that machinery also gives something. Quantitatively, I'm not quite sure what you get, but something. Quasi-polynomial.
Any other questions? All right, then we continue at 4 o'clock.